Okay, we've established that the kernel of a homomorphism is a normal subgroup of our group G. Phi maps G to H is a homomorphism. The kernel of that homomorphism is the set X such that phi of X equals the identity, and phi of X, phi of Y equals phi of X, Y. What I'm going to do now is go the other way. I'm going to start with n being a normal subgroup of G, and I want to show that, prove that n is the kernel of some homomorphism, which I'm going to cook up. So we're going the other way. So what we've got is a kernel of a homomorphism is a normal subgroup, which we've proved. And now I'm going to say take any normal subgroup, that is the kernel of some homomorphism. So we're beginning to see that normality, or being a normal subgroup, is quite a profound notion. What I'm going to do is I'm going to map G. What I want to do here is, let me just remind you how a group is set up. There's my group G. And we've got N is a normal subgroup of G. So these are the cosets here. They're all drawn in a rather peculiar way. It's supposed to be the same size. These are all cosets, and I'm going to write them as right cosets. So that's the identity coset. There's X, Y, Z. I'm going to run out of letters. B, C, D, and E. And of course, these are left cosets and right cosets. So what I'm going to do, sorry, these are left cosets and right cosets. So I've just written it like that, but I could just as easily have written it like that because they're the same, because n's normal. But I've written them as right cosets, but I could have written them as left cosets. So what I'm going to do, I'm going to map G to the set of cosets. Yeah. So what am I going to take? Well, it's to the set of cosets. So what I want to do is take an element of G, and I'm going to map it to one of the cosets. So I'm going to take X, and I'm going to map it to f of X equals one of the cosets. One of the cosets. So there's quite a lot going on here. I'm going to pinch that in a bit. And I'm going to say f of X equals nx. Well, alright, that's great. But I also need, remember I'm mapping f maps G to H. I need a group operation on H. We've got one here. We've got one here already. We've got one here because that's the group we started with. But we need one here, or we need to verify at least that its group operation is correct. So we need to do that. We need to make sure that that's well defined and make sure that it satisfies the axioms of a group. And then we need to show separately that F is a homomorphism. Okay, and I'm going to do those in two separate sections. There's a lot going on here. There's a lot going on here. This is complicated. So we've got a normal subgroup. What I'm going to show is that it's the kernel of some homomorphism. Alright, and I'm going to split this up into different screencasts because I think they're getting too long. I'm not sure how long this one is. I haven't got a little clock with this one, but I'm going to stop here and I'm going to prove these two bits separately. Okay, stop there.